Hey, hello, 123 students. I got a question about a hard one here, number 66, at near the end of your homework assignment. So I thought maybe I would kind of work through this one because I didn't have a video on this one, and this is a really hard one. And maybe I'll show it in two different ways. I hope that doesn't take too long. We'll see how the time goes. But let's look at this one. I decided to print it up. It says here that one slit of a double slit is wider than slit number 2, so that the light from slit number 1 has an amplitude that is 3 times that of the light of slit number 2. Show that the equation 37.14 is then replaced by this equation. Okay, so we'll come back to that, but this is what we're shooting for, and this is a little different than anything we've done. That's why it's a hard problem. Let me go back to what we did do. What we did do is we made a double slit experiment like this. We said, okay, so you've got light coming in from these two slits. If we call this lower one slit number 1, the light will spread out. And then also, same thing, if we call this slit number 2, the light spreads out. And then if we look over here on a screen and we measure things from down the center here, and so maybe we go some distance away. I'll just do like I did in class. I'll go up. I was debating to go up or down. I'll just call this point P. So the light travels along this path from slit. Oh, I can't remember if I called that 1 or 2. Let me just call it 1. I'll label it here 1. And then we go along this path, so we'll call that slit number 2. And you can see that the path from number 2 is a little bit farther than number 1. But what we said in class then is if you wanted to figure out the intensity on the screen, you would first need to look at the interference, the constructive and destructive interference pattern. So what we would say here is we would say, okay, wave number 1 hitting the screen might look something like this. Since it's an electromagnetic wave, we might say that it has E for electric field. From number 1, it might have some value of E naught, and then sine, and it would travel over to this point P, so we would say it would be a kx minus omega t. And, of course, we'll just call where it hits 0 phase, because wave number 1 could be mathematically written like this, E naught. And the difference between the two waves would be that wave number 2 travels a little bit further and therefore is out of phase compared to the first one. And then we would add those two together. But let me pause right here. I don't want to completely do just the double slit, but I wanted to point out right there that when we did the double slit experiment and we added these two waves together, we said that they would have the same amplitude. That implied that either the holes were the same size or the intensity of the light on the lower half was different from the upper half. Now, in our problem, that's the key difference. See, it says slit number 1 in a double slit is wider than slit number 2, so that the light from slit number 1 has an amplitude that is 3 times greater. And that's going to be the difference. Is for slit number 2, I'm going to end up putting, for slit number 2, it'll be 1/3 of the value. Slit number 2, so that the light from slit number 1 has an amplitude 3 times greater. So this amplitude, number 1, is 3 times greater than number 2. And so that's what's going to change between what we did in class and then what we're about to do. But I wanted to remind you of that because what we did then is we said, okay, let's look at the total. And so if we called this wave 1 and wave 2, we then said wave 1 added to wave 2. In other words, we added them together. Then we said the intensity is then proportional to the square of the total amplitude. So what we have to do is first add amplitudes together, get that number and square it to get the intensity. So again, without doing the same thing we did in class or in the book, just note that what we're about to do is a lot harder than what we did in class, because in class, when we had something that looked like this, we just said, well, this would just be E naught sine kx minus omega t, and the same amplitude. And the reason the same amplitude was kind of nice is because then you can just factor out the E naughts. And if you called this then A and this angle here B, you really have the sine of A added to the sine of B. And that's a very common trig identity. And so in class, we just said, all right, if you have sine of A plus sine of B, that's 2 times, and it's cosine of the difference. And it doesn't matter which order you put them in, but I'll just put them as A minus B over 2 times the sine, and then you would add them together, A plus B over 2. So that's what we did in class. And again, let me not go all the way through what we did in class, but we used a very common trig identity, sine A plus sine B, and we can do that because it had the same amplitude. Okay, so here's what's going to be dramatically different. When we go to do this problem, we have a sine A and then something that is a amplitude difference by a factor of 3. And so we don't have this simple trig identity, sine A plus sine B. So instead, we need to look up a trig identity, or we need to know something about the mathematics of phasors. And so maybe I should use this as an opportunity to show you some more advanced mathematics called phasors, something that you will get soon. And so it couldn't hurt to throw this in the video, but I'll just make it that much longer. But I'll put that towards the end in case any of you are uninterested in going into some new mathematics. But what I need to do then, before I get started really doing this problem, is to look up some trig identity. So I did that, and I printed it here. And here is the arbitrary phase shift. So the more general one, if I have some amplitude A sine with a phase added to some amplitude B with a phase, this is what it equals, where C is given by this parameter and this phase angle is given by this parameter. So I'm going to take advantage of the arbitrary phase shift with arbitrary amplitudes, because that's what I'm going to need to solve this problem. So let me keep this sheet handy, and now let's actually begin this problem. And I hope my kind of review of the double slit wasn't too long, but that's what this is springboarding off here. All right, so now let's actually look at this problem. So here I'm going to make a double slit. I'm going to put the screen here. But as it says, slit 1 is a little bit wider, such that the amplitude is 3 times as much. So kind of going through the same logic that the light's going to spread out. And then the second slit, the light's going to spread out. It's going to hit this point P. But when I write down these two waves, let me call this wave number 1, so E1. And I'll just take this first one as an E naught, and then sine kx minus omega t. And here's where we kind of differ from what we did with the double slit. Let me write number 2 as E naught over 3 sine kx minus omega t with some additional phase. So a different amplitude as well. Maybe I'll pull back this first discussion we had. See, so I'm just doing the same thing as the double slit. I got my two waves, field 1 and field 2, and I'm going to add them together. But right here is where it differs between what we did in class and what we're about to do in this problem, because here the second one has an amplitude 1/3. Now, of course, it is also off by a phase, depending, where you are on the screen. And we can talk about that phase. But as you remember from the double slit, the actual discussion of that phase wasn't important. It was the combining of the amplitude. So we're really not even going to need to focus on that phase. So that'll be good, because if you remember that arbitrary trig identity, here's the amplitude of it, and here's the phase of it. And so the phase is kind of complicated, and I'm kind of looking forward to the fact that I don't have to really analyze that very much. I just have to analyze the amplitude. Okay, so let's actually then see what the total electric field would look like when you added these two waves together. So this is that principle of superposition, and it just says add wave 1 with wave 2. So in this case, wave 1 is E naught sine kx minus omega t. And wave number 2 is E naught over 3 sine kx minus omega t and some additional phase, phi. Okay. And again, not proving this trig identity, but just looking it up in a book here. I know our Appendix B doesn't do the general one, so I had to go to my math book and look this up. And here's what it's saying. So in my case, I guess I would call little a E naught and little b E naught over 3. And why don't I call, well, I should have wrote that one first. Why don't I call the x the kx minus omega t, so they both have that piece of the puzzle. This theta a doesn't even exist here, so that I guess would be 0. And theta b would be my phi. Okay. And so what it says then is to put these two together, you would get this amplitude c, okay, and then you would get sine, and then there's that x, which we would call it kx minus omega t, and then there would be some script phi phase angle, which would be that crazy stuff. But let me, like I said, justify that. I don't have to worry about all that. But let me just do the trig identity. And so C would be the square root of all of this. So square root of, looks like I got a lot to fit in there. And then it would be a sine kx minus omega t plus this kind of this script phi. And like I said, I don't think I even need to mess with that. That's a good thing. So let's look at this amplitude. Let's see. It would be a squared. And so a squared would be E naught squared plus a b squared. Okay, so b squared would be E naught over 3 squared plus a 2 and an A is E naught, and a B is E naught over 3, so 2AB. And then cosine, just going to fit here, of theta A, remember theta A is 0, okay, minus theta B, which is phi. So let's just minus phi. Okay. All right. So there is the, and I can simplify the math here, but this is equal to those two combined together. Let me move down a little bit, give me some more space here. But I want to come back to what I said about the double slit. So let's come back to this first page here. I had said to get the intensity, you just have to say it's proportional to the field squared. So in other words, it's proportional to the amplitude squared. This is the part that I was saying that I can just say A or I equals, and then let me just focus on this piece. This is the amplitude, and let me square it. So that's why I was saying I don't need to really even focus on that. That's the part when we did the double slit that I said, we talked about how quickly this would be, right? This would be a frequency in hundreds of terahertz, which means your eyes or your camera would just get an average effect when you square it. And so sine squared, the average is 1/2. So that falls into the category of just kind of averaged out over time. And this is the real piece. And then fortunately, when you say it's amplitude squared, we have this square root. So this would just say that the intensity is equal or proportional to, and I'll just get rid of the square root. So I get an E naught squared. I get an E naught squared over 9 when I square that one. Here I get a 2/3 E naught squared. And I'm also just going to drop the negative sign in the cosine function because cosine's an even function. So cosine of negative phi is the same as just cosine of phi. Okay, and then clearly these are like terms, so I can add them together. The common denominator would be a 9, so that would be a 9 plus a 1. That makes 10 E naught squared, and this makes 2/3 E naught squared cosine phi. Now, personally, I would probably stop there. I kind of like that as my final answer. However, the author says to show that it comes out to be this thing. And if you'll notice, it doesn't have a cosine phi. It has a cosine squared and has a phi over 2. So there's some kind of half-angle identity that they're using that they prefer. And again, if you remember, since we're comparing it to equation 37.12, which said the intensity was the intensity I naught cosine squared phi over 2, I think they're just trying to manipulate this equation so that it has kind of the same form. And so it looks like a way that you can compare the intensity of this scenario with the intensity of the double slit where the light coming through both openings was the same. So, like I said, if I was doing this in practice, I'd probably just leave this here. I think this is probably a nicer form. But if I wanted to compare it to the double slit, I probably would want to write this then as a cosine squared phi over 2. So let's do that. Let's use one of those half-angle trig identities. And I had printed that one up too, just in case those aren't quite as memorized as some of these other ones. But the half-angle formula. And here it is. It's basically saying right here that if you have cosine theta over 2 plus or minus, it's got this square root. Let me rearrange this by first squaring it. So this would be cosine squared theta over 2 equals 1 plus cosine theta over 2. And then let me just solve this for cosine theta. And if I did that, I would bring the 2 over and then subtract the 1. So this is how I can turn a cosine theta into its half angle. And then in the process, there's a square of the cosine function. And then some other stuff going on here. So that's what I'm going to put right here. And so this is going to be a 2 times a cosine squared phi over 2 minus 1. So there's the trig identity. All right, now simplifying this a little bit, I'll take the 10 over 9 e naught squared. Right here, this 2 times that 2 is a 4/3 e naught. Let's see, 4/3 e naught squared, cosine squared, phi over 2. And then this piece right here would be minus 2/3 e naught squared. All right, maybe I should call this page 2. Okay, so moving on to page 3 then, you can see here that this first and third term are like terms. So let me just get it to a common denominator. So this would be a 4 over a 9. So a 10 minus a 4. Oops. My apologies. If I multiply by 3, I'd get a 6. I guess in my head I was squaring. Sorry. But glad I caught it. But the common denominator I'd multiply by 3, so I need to multiply this by 3. Okay, so 10 minus a 6 is a 4 over 9 e naught squared. And then plus 4 over 3 e naught squared cosine squared phi over 2. And you can kind of see that there's some common factors. For example, each of these have a 4 and an e naught squared. Looking at where he wants us to go with this, it looks like he has a common factor of a 9 too. So I'm gonna factor out a common 9, leaving that with a 1. But that's not really a 9. I mean, we can write it as times 3 times 3. Then we get a 9 in the bottom. But that means we're left with a 3 in this numerator together with the cosine squared phi over 2. And now I think we have it. I think we're finally there. I guess the last step, which I don't really like either, he calls this I max. And so he says E naught squared is I max. And that's not how I would define I max. So I'm not real happy with that notation. I would call I max the intensity when you go straight down the middle with both slits open. If you do this E squared is I max, coming back to our beginning, you're really saying that's the intensity that you would get from, just the one bigger slit, not down the center when both of them are open. So I'm not a big fan of his definition of I max, but let me use it that way. Okay. Anyways, and then we get what we want. Yay! And so here we are. So I hope that wasn't too long. Had some trig identities, but hopefully it also helped to see how this hard problem really was asking you to repeat what you did for the double slit, or what we did for the double slit in class and in lecture, but then to take it one step further. So it is a hard problem. So I hope that helped. Now, I said I would show you some really neat mathematics. And I've been going here for 25 and a half minutes. Why don't I just real quickly show you the quick phasors? Any of you who are still listening, you can continue to listen on here. But phasors are a nice mathematical tool because, to be quite honest, memorizing this is just not natural. And if you try to memorize all of these, you just end up forgetting them here and there. And so what's neat about the mathematics of phasors is we can derive all of these really simple. Now, not the identity itself, but we could do this problem without having to look this up if we know the mathematics of phasors. All right, so phasors. Ooh, what's a phasor? Well, let me kind of take you probably way, way back to your very first day in trigonometry class and really ask, what is sine x? I mean, where did this idea come from? I mean, usually in a class, a trig class, you'll see this wavy looking thing. We call it a sine wave. And we really ask ourselves, well, what the heck is that? And probably on the first day of your trig class or the first chapter, it was explained to you kind of the geometry behind it. But then it was just kind of forgotten about it. And so that's really what I want to begin with, is taking you way back to the fundamentals. And here's the fundamentals. It starts with a unit circle. So I think you probably remember the idea of a unit circle. So let me kind of draw a circle of radius 1. And the ancient, I was going to say ancient Greeks. I think it was the ancient Greeks, not real sure. But some ancient civilization said, what would happen if you just tied a string right here at the beginning of the unit circle and you just started wrapping the string around the unit circle? And as you were wrapping it, you made a little plot. And that plot was how long is the string on the x-axis and what is the height of it on the y-axis. Okay, so at the very beginning, the length of the string is 0. It's how much you've wrapped so far, and it's at a height of 0. And you start wrapping it or laying it down, and you then get higher and higher and higher. And at first it climbs very quickly, and then eventually it climbs at a lower rate as it gets up the hill. It gets to the top of the hill, and since it's a unit circle, it goes up to 1. And it would be the length of a quarter of a circle. Now, this is a unit circle. So remember, the length of an arc is the angle times the radius. Or in this case, since the radius is 1, it's just the angle in radians. So in other words, if you put a string of length pi over 2, you would go up height 1. Well, if you keep wrapping the string, by the time you get to a length of pi, you have now come down the hill, and you are now at a height 0. and it then just repeats on the lower half and goes to a height of -1 when you finally wrap all the way around the circle. And so the string has a full length of 2 pi, and it just keeps repeating. All right, so like I said, you may have forgotten this fundamental principle of the sine function, but phasors take advantage of it. And so phasors turn trig functions into geometry. And usually calculating lengths in terms of geometry are much easier to remember and to work with than the trig identities. And so you will see here in a moment that I will be able to do this problem without looking this up, without memorizing a trig identity, because I'm going to do some geometry. Well, I might even throw some simple right-angled trig just to make my geometry easier too. So, but it won't be any of the harder trig identities. Okay, so what is a phasor again? All right, so here's the way you might think about a mathematical function that looked like this. Sine kx minus omega t. For simplicity, let me just call that A. Okay, so this would be sine A. Now, you could then say something to this effect. Instead of thinking of sine A as being this curve that goes up and down and up and down and up and down, you could think of it as a point at the tip of a circle that goes around and around and around and around. And it doesn't even have to be a unit circle. If you put then an amplitude in front of it, this then would be the radius. And so if I made a bigger radius here of 2, then it would go up to a 2 and then back down and down to a -2. And so what I can now do is think about sine functions not as this wavy thing that goes up and down, but as a little point on a circle that's moving, where the radius of the circle is the amplitude of the trig function. Let me show you. So if I just had sine A, the amplitude in front would be 1, and so if I imagine going out 1 unit and then moving around a circle, where the distance I moved, and I want to be careful when I say the word distance, I really mean the angle I moved, is that A. And in this case, the A changes with space and time. And so I'm just going to kind of imagine in my mind a little arrowhead pointing to the circle, and it's just kind of spinning. And the vertical height is the sine of that function. And so I just have in my mind, instead of this wavy thing, I have this little arrowhead that sticks out and goes around. Now, maybe in a different color, I should emphasize that I don't have to have a unit circle. If I had something that had an amplitude of 3 sine A, I would draw a circle that would be 1, 2, an amplitude of 3, and it would just go around. And so I would imagine kind of this little arrowhead sticking out and moving around. And if I can just mentally follow that little point on the circle, and then wherever that little point is, let's say here, so let's say the arrowhead's pointing here at that moment, I can just project back, and that would be the value of the sine. So again, what I'm trying to do is give you a visual picture of a trig function. I'm trying to change a trig function, this wavy thing, into a moving circle. And then the position of it now becomes geometry. And that's how I'm going to change a trig function and adding two trig functions together into geometry and just adding two arrowheads together. That's going to be the power of this. All right. So if we try to do this same problem with phasors, okay, let's come back to how we got started this problem. And I guess I don't mean started in the sense that I was reviewing the double slit, but when I actually started this problem, where I had two trig functions that I wanted to add together. So this was the start of page 2. And they had different amplitudes. And they had a different phase. I just wanted to add them together and get the results. And of course, what I did, I just looked up the trig identity and finished it. But I claim that I don't even need to look up the trig identity. I could add these together really easy doing a mental picture of phasors and hopefully come out with the same thing. Again, yeah, talking a lot. It's a long video, but it might be nice to see because it's something that's usually considered something that you do a lot of in your third year of college, which will be when you guys transfer. And many of you are right there. You're getting ready to transfer. And so you're getting ready to start your third year. Next fall, you will be at, and you will leave us and go on and hopefully be successful wherever you transfer to. And you'll start doing phasors a lot. They're a very, very handy tool. But again, they're considered a third year, and that's why you haven't seen them yet. And that's why I thought I would babble on and maybe address these a little bit. Okay, so let me see if I can help you solve this problem, not using a trig identity, but using two phasors. So let me start with this one. Let's look at this first one. How would you view something with an amplitude of E0 sine using a phasors? Well, I guess you would make a unit circle. No, sorry, not a unit circle. A circle that has a radius of E0, and you would imagine it as maybe a little arrowhead. So I'll start with a little arrowhead here. And imagine that spinning around. All right, so that's visually what's going on in my mind when I think of this one. Okay, now how about this one? Well, this one, as a phasor, would have an amplitude 1/3 as the size. It would spin around kind of with that same phase, but it starts with a little something extra. So 1/3 of the length would be maybe about here. And so let me draw a circle to it. And let me draw that phasor with a starting angle of phi. So in my mind, what I have is I have one that starts at an angle of 0 and then grows, because these two together I'm just going to call A, and that's the part that represents as this red one is spinning. But then the second one here has the starting point, so it's going to spin, but it starts off with an initial phase. So it has an initial phase and it spins. So in my mind, to kind of visualize this phasor, without the unit circle, I have the arrowhead starting here for the red one, and for the green one starting about like this, and then the two move, and they move together. See, they have the same A. So one thing about this particular phasor one is they move together. So in other words, some moment in time, this red one's going to be maybe right here. But this green one will have moved the same amount. And so the angle between the red one and the green one is still this extra starting phase. So they move together. And that's the key to this. Because if we kind of mentally get rid of the movement, which that's actually kind of hard. It's the movement that I'm probably having hard showing you in this video because I'm drawing static pictures and to see them rotate is kind of hard, and I got to explain that on a piece of paper. But watching these mentally spin in my mind and also adding them together like you would a vector head to tail, watch this. Let me take the initial red one and draw it out to here. Let me take the initial green one, and instead of writing them tail to tail, two additions tail to tail, which is hard to see the sum of the two. This really goes back to the beginning of this whole physics sequence when we added vectors. Sometimes we like to add vectors or show vectors tail to tail because you can see the angle between them, and that's what I've done here. But other times we like to draw vectors head to tail, because when you do that, you see the sum of them much better. And so this blue would represent the sum of the two. Now remember, then this would be the angle phi between them. And that's why when you draw them head to tail, it's kind of hard to see the angle between them because it's kind of outside. So drawing vectors tail to tail is nice because you can see the angle between them. But drawing them head to tail is nice because then you can see the sum of them. So the blue is the sum of them. And that's what I'm looking for. I'm looking for the sum of these two. So it's kind of neat to imagine that if I'd drawn the blue one on here, the sum of these two would look something like this, and it would stay that way as it arced around. So if you just want to know the amplitude of it, you can find it at time equals to 0 and realize that as time goes on, this would just kind of move around. And so the blue one would have the same rate going around that the green and the red one have. And that's exactly what this trig identity is saying. If this is an x, that's the x here, the resulting goes around at the same rate, x. Now, it'll have some phase that depends on all of this, and it'll have some amplitude that depends on the individual amplitudes and the angles between them. And that's what we're going to see in this geometry. So if I was doing this problem and I knew phasors, I would have done it this way. I would have just drawn a grid. I would have drawn phasor number 1 and said this right here has a length of E0. That would represent this. And so I would say wave number 1 is visually represented right there with E0. And wave number 2, which has an amplitude of E0 over 3, is represented in green. And this then is the equation for it, but this is the visual picture I have. And so to get the amplitude, the total of this, I would just use Pythagorean's theorem. I would say how far in the x, how far in the y, and square it. So E squared, and I'll just say is x squared plus y squared. And so what's x? It's E0 plus how much of the green one is in the x direction. Well, that would be an E naught over 3 cosine phi. So that's how I would get the x on this phasor diagram. And for the y, well, the y is pretty easy. Only the green one has a y component, and it would be E naught sine phi squared. And then, since I am after the field squared, I'd actually square this. So here I would have an E naught squared. This one would be, let's see, 2 times these two multiplied together, E naught squared over 3 cosine phi. And then this squared would be E naught squared over 9 cosine squared phi. So that's what happens when you have a plus b and you square it. You get a squared plus 2ab plus b squared. And then this one squared is real easy. This is just E naught squared sine squared phi. And then if you take a look, we've got this cosine squared and this, and I'm sorry, this should have been over 3, shouldn't it? This would be an E naught over 3. It'd be the length of the green one, and then squared, because that needs to be over a 9, because those would match. And cosine squared and sine squared are 1. So this would be E naught squared plus, and then grouping these together would just be E naught squared over 9. And then this would be 2 E naught squared over 3 cosine phi. So that's how I would get the intensity if I knew phasors. Notice, all I did was draw a picture and then look at the x component, look at the y component, use Pythagorean's theorem, and now I got the intensity. There is the square of it. Now, I've got some simplifications to do, but let me point out that what I have right now is exactly what I got at this point after I had talked about this trig identity. And so look how easy that would be with phasors. And so phasors is a very, very powerful mathematical tool, and that's why I thought I would take some extra time and throw that out there for anybody who's bothered to listen this long. All right, well, I'll stop it here and hope you guys have a good day. Bye now.